Right now, as you hear these words, you are orbiting a thermonuclear bomb 50 times larger than the planet beneath your feet. This bomb has been detonating continuously for 4.6 billion years. Every second, it converts 600 million tons of hydrogen into helium, through a process so violent that it would vaporize Earth instantly if we drifted just 3 million kilometers closer. The explosion is contained only by gravity so intense it warps the fabric of space-time itself. We call this bomb the Sun, and it is the reason you are alive. But here is what they never told you in school. The Sun is not special. It is not unique. It is merely one configuration of stellar violence in a universe that has invented 7 distinct ways for gravity to murder matter. 7 different mechanisms for turning clouds of gas into cosmic furnaces. 7 categories of stellar predator, each operating according to its own brutal physics. And every single one of them is staring at you right now, through the darkness between worlds. The night sky is not peaceful. It is not serene. When you look up and see points of light scattered across the void, you are witnessing an endless war. Between gravity and pressure playing out across distances so vast that light itself takes years to cross them. Each star is a battlefield. Each twinkle is a flicker in a thermonuclear inferno that has been raging since before your species existed. And the terrifying truth is this: the rules are different depending on which type of star you are looking at. Astronomers discovered this in the 1890s when Annie Jumpcannon at Harvard Observatory began cataloging stellar spectra and noticed something impossible. Stars were not all the same. They came in distinct varieties, organized by temperature, by color, by the violence of their internal fusion processes. She created a classification system so precise that it is still used today, more than a century later. The system uses 7 letters: O, B, A, F, G, K, and M. Generations of astronomy students memorized them using the mnemonic, "Oh, be a fine girl, kiss me." But that innocent phrase conceals a hierarchy of cosmic violence that determines the fate of everything in the universe, including you. Type O stars burn at temperatures exceeding 30,000 Kelvin. They are blue-white monsters that consume their fuel so rapidly. They live for only a few million years before exploding in supernovas that forge the heavy elements necessary for planets and life. Type B stars are slightly cooler but still ferociously hot, blazing at 20,000 Kelvin and radiating ultraviolet light intense enough to ionize entire nebulae. Type A stars are the brilliant white stars that dominate our night sky, including Sirius, the brightest star visible from Earth. Type F stars are yellow-white transition objects, caught between the fury of A-class stars and the relative calm of G-class stars like our Sun. Type K stars are orange dwarfs, cooler and longer-lived than our Sun, potentially the best hosts for habitable planets in the galaxy. And finally, Type M stars are the red dwarfs, the most common stars in the universe, faint and cool but so long-lived. They will still be burning trillions of years from now, long after our Sun has died. Each type represents a fundamentally different stellar environment. A different balance between gravitational collapse and fusion pressure, a different lifespan, a different chemical signature, a different fate, waiting at the end of stellar evolution. And here is where the cosmic horror begins to reveal itself. The type of star you orbit determines everything. It determines whether planets can form, whether those planets can harbor liquid water, whether life has time to evolve before the star dies, whether that life survives long enough to develop intelligence, whether that intelligence has any hope of escaping its solar system. Before the star that birthed, it becomes its executioner. Humanity developed around a Type G star, a yellow dwarf in the middle of the spectral classification. Burning at 5,700 Kelvin, with a lifespan of roughly 10 billion years, we appeared in the last half-billion years of a 10-billion-year stellar life cycle. We evolved in the narrow window between our star's violent youth, when solar flares could have sterilized Earth's surface, and its inevitable expansion into a red giant that will consume our planet entirely. We are the children of a cosmic coincidence. Living on a world orbiting a bomb that happens to be detonating at exactly the right rate to keep us warm without incinerating us. But most stars in the galaxy are not like our Sun. 76% of all stars are Type M red dwarfs, cool and faint, and prone to violent flares that would strip away the atmospheres of any nearby planets. 12% are Type K orange dwarfs, slightly cooler than our Sun, but potentially better hosts for long-term habitability. Only 7.6% are Type G stars like the Sun. The hot, massive O and B type stars that create the most spectacular nebulae and supernova remnants, they represent less than 0.13%. Of all stars, they are cosmic anomalies, brilliant monsters that burn out almost as soon as they are born. This distribution reveals something terrifying about the universe's priorities. The cosmos does not care about spectacle. It does not care about creating conditions for life. It cares only about efficiency, about stretching fusion reactions across the maximum possible time span. The universe prefers dim, cool, stable stars that will burn for trillions of years over hot, brilliant giants that explode after a few million years. And this preference has consequences for everything. If you were born orbiting a Type M red dwarf, your world would be tidally locked, with one hemisphere permanently facing the star, and the other frozen in eternal darkness. The habitable zone would be so close to the star that your planet would be bombarded by flares. If you were born orbiting a Type O star, you would not be born at all because the star would die before multicellular life could evolve. And the radiation environment would be so extreme that complex organic chemistry would be impossible anyway. The stellar classification system is not just a cataloging tool. It is a map of cosmic possibility. It defines the boundaries of where life can emerge, where intelligence can develop, where technological civilizations might arise to look back at their parent star and realize what it really is. And that realization is always the same. Across all possible worlds orbiting all possible star types, every star is a temporary phenomenon. Every star is dying. The only question is how fast. The 7 main types of stars represent 7 different timescales of stellar death. Type O stars die in supernova explosions after just a few million years. Type B stars last 10 to 100 million years before meeting similar fates. Type A and F stars burn for 1 to 3 billion years, dying in less spectacular but still violent planetary nebula events that expose their white dwarf cores to the cosmos. Type G stars like our Sun will swell into red giants in 10 billion years, consuming their inner planets before shedding their outer layers and leaving behind white dwarf remnants. Type K stars will live for 15 to 30 billion years, outlasting every G-type star that currently exists. And Type M red dwarfs will continue burning for 100 billion to 10 trillion years, long after every other stellar type has burned out. This script will take you through each of these stellar categories in detail. You will learn how astronomers discovered the classification system. By analyzing the light signatures of hundreds of thousands of stars, you will understand the physics that determines why some stars burn blue and hot, while others glow red and cool. You will see how stellar mass dictates stellar fate, how a difference of just a few solar masses separates stars that will die quietly from stars that will explode with a force of 10 octillion megatons. You will learn which types of stars are most likely to host habitable planets and which are most likely to destroy any life that attempts to evolve in their vicinity. But more than that, you will come to understand what it means to be a temporary pattern of organization in a universe that uses stars as its primary mechanism for converting hydrogen into heavier elements. Every atom in your body, heavier than helium, was forged in the core of a star and scattered into space when that star died. You are stellar debris that has temporarily organized itself into a configuration capable of contemplating its own origin. And the star that currently sustains you is on a clock that cannot be stopped, cannot be reset, and cannot be extended. The violence is not coming. The violence is already here. It is happening right now, 93 million miles away, at a rate of 600 million tons per second. The only reason you perceive it as gentle sunlight instead of instant annihilation is distance and the laws of thermodynamics. But those same laws guarantee that the violence will change. In 5 billion years, our Type G star will enter its red giant phase. expanding to consume Mercury, Venus, and possibly Earth. The oceans will boil away. The atmosphere will be stripped into space. The crust will melt and vaporize. And there is nothing anyone can do to prevent this, because it is written into the fundamental physics of stellar evolution. If you enjoy learning how the universe has constructed 7 different varieties of thermonuclear time bomb and installed them throughout every galaxy, hit that like button. If you want to understand which type of stellar predator is most likely to host life and which is most likely to destroy it, subscribe to this channel. Because what comes next will change how you see every point of light in the night sky. The 7 types of stars are not just categories in an astronomy textbook. They are the 7 mechanisms through which the universe converts matter into energy. And energy into the heavy elements necessary for planets, for life, for consciousness itself. They are the 7 timers counting down to 7 different varieties of cosmic death. And understanding them means understanding the temporary nature of everything that depends on stellar fusion for survival. Prepare yourselves. We begin with the most violent stars in the universe. The most dangerous stars in the universe are invisible to human eyes. This is not a metaphor. This is physics. Type O stars emit most of their radiation in the ultraviolet spectrum. Wavelengths shorter than 400 nanometers that your retinas cannot detect. When you look at the night sky with your naked eyes, you are seeing an artificially dimmed version of reality. The most violent stellar objects are hidden from you by the limitations of your biology. And this is fortunate because if you could see Type O stars, as they truly are, blazing at their full intensity across all wavelengths, you would understand immediately how fragile your existence is. Type O stars are defined by surface temperatures exceeding 30,000 Kelvin. For context, the surface of our Sun reaches only 5,700 Kelvin. Type O stars are more than 5 times hotter. Their cores operate at temperatures approaching 200 million Kelvin, hot enough that helium fusion begins almost immediately, creating what astronomers call the CNO cycle, the carbon-nitrogen-oxygen fusion process that powers the most massive stars in the universe. The energy output is obscene. A single Type O star can be 1 million times more luminous than our Sun. It pumps out more energy in 1 year than our Sun will produce in its entire 10 billion year lifetime. The first Type O star ever identified was Theta 1 Orionis C, located in the Trapezium cluster, at the heart of the Orion Nebula, approximately 1,340 light-years from Earth. Astronomers discovered it in the 1890s. During the same spectroscopic surveys that revealed the stellar classification system, when they analyzed its light signature, they found something unprecedented. The star was so hot that its spectrum showed ionized helium lines, features that only appear when temperatures exceed 25,000 Kelvin. This was evidence of a stellar environment so extreme that electrons were being stripped away from helium atoms, atoms that are normally difficult to ionize. Theta 1 Orionis C is not alone in its violence. The star Zeta Puppis, located 840 light-years away in the constellation Puppis, is another classic Type O star. It burns at 40,000 Kelvin. It has a mass 40 times greater than our Sun, and it is currently in the process of dying, having already burned through most of its hydrogen fuel and begun fusing heavier elements in its core. Zeta Puppis is what astronomers call a runaway star. It was ejected from its birth cluster millions of years ago, possibly when its binary companion exploded in a supernova. Now it travels through space at 60,000 kilometers per hour, plowing through the interstellar medium and creating a bow shock wave visible in infrared wavelengths. This star is a cosmic bullet, and it will detonate in a supernova within the next 100,000 years, an eye blink in cosmic time. But perhaps the most famous Type O star is Zeta Ophiuchi, also a runaway star, also traveling at supersonic speeds through the galaxy, also creating a massive bow shock as it compresses the interstellar medium ahead of it. Zeta Ophiuchi is located 366 light-years from Earth. It has 20 times the mass of our Sun. Its surface temperature reaches 34,000 Kelvin. And here is the terrifying detail. Zeta Ophiuchi was once part of a binary system. Its companion star was even more massive. That companion died in a supernova explosion roughly 1 million years ago, an explosion so violent. It kicked Zeta Ophiuchi out of its orbital path and sent it careening through the galaxy at 24 kilometers per second. Think about what this means. Binary star systems containing type O stars are common because these massive stars form in clusters, where gravitational interactions naturally create binary pairs. But type O stars live fast and die young. The more massive star in the binary system will always die first. And when it explodes, the blast can be powerful enough to disrupt or destroy its companion. Zeta Ophiuchi survived its companion's death, but it was transformed into a runaway star, a stellar refugee fleeing the scene of a cosmic catastrophe. The violence of type O stars is not limited to their eventual deaths. These objects are dangerous throughout their entire brief lifetimes. They generate stellar winds so powerful they strip away 10 to the power of -6 solar masses per year. Material that streams away from the star at velocities exceeding 2,000 kilometers per second. For comparison, our Sun loses about 10 to the power of -14 solar masses per year through solar wind. Type O stars shed material 100 million times faster than our Sun. This wind is not gentle. It is a hurricane of ionized particles moving at a significant fraction of light speed, powerful enough to shape the structure of nearby nebulae, and compress clouds of gas until they collapse into new generations of stars. Type O stars also emit prodigious amounts of ultraviolet radiation. Photons energetic enough to ionize hydrogen atoms across vast regions of space. When you look at images of nebulae like the Orion Nebula, those glowing red regions are hydrogen atoms being excited and ionized by ultraviolet light from nearby type O stars. The stars are essentially cooking the nebulae, heating the gas to 10,000 Kelvin and creating what astronomers call H2 regions, zones where hydrogen exists in its ionized state. These regions can span hundreds of light years. A single type O star can ionize a bubble of space larger than the distance between our Sun and the nearest stars. The formation of type O stars requires special conditions. You cannot create a 40 solar mass star through gentle accretion processes. The protostellar disk would generate so much radiation pressure as material falls inward that it would blow itself apart before reaching stellar ignition. Somehow, nature overcomes this problem. The leading theory involves competitive accretion in dense stellar clusters. When hundreds or thousands of protostars form in close proximity, they compete for the available gas supply. A few lucky protostars in the cluster center manage to accrete material faster than their neighbors, growing massive enough that their gravity can overcome radiation pressure. But even this process is violent. Computer simulations show that massive star formation involves disk fragmentation, gravitational instabilities, and possible mergers between smaller protostars. The growing type O star experiences episodes of rapid accretion, punctuated by violent outbursts, as material crashes onto its surface at supersonic velocities. The mass range for type O stars spans from 16 solar masses to potentially hundreds of solar masses. The most massive confirmed star currently known is R136A1. Located in the Tarantula Nebula in the Large Magellanic Cloud, this monster contains approximately 265 solar masses. Its surface temperature exceeds 50,000 Kelvin. Its luminosity is 8.7 million times greater than our Sun. And it is losing mass so rapidly through stellar winds that it sheds the equivalent of Earth's mass every 10,000 years. R136A1 challenges theoretical limits on stellar mass. Astrophysicists once believed that stars could not exceed 150 solar masses, because radiation pressure would overcome gravity and blow the star apart. Yet R136A1 exists. It is stable, at least for now. The lifespan of a type O star is measured in millions of years, not billions. A 16 solar mass O-type star will burn through its hydrogen fuel. In approximately 10 million years, a 40 solar mass O-type star lasts only 1 million years, the most massive stars, exceeding 100 solar masses, may live for only a few 100,000 years. Compare this to our Sun's 10 billion-year lifespan, and you see the price of mass. But Type O stars do not die quietly. They die in Type 2 supernova explosions, detonations so powerful they release more energy in a few seconds than our Sun will produce in its entire lifetime. The mechanism involves core collapse. Once a Type O star exhausts the hydrogen in its core, it begins fusing helium into carbon and oxygen. Then it fuses carbon into neon and magnesium. Then neon into oxygen and magnesium. Each stage of fusion produces less energy and lasts for a shorter time. Hydrogen fusion might last 1,000,000 years. Silicon fusion lasts approximately 1 day. Eventually, the star's core consists of iron, and iron is the end of the line. Fusing iron nuclei requires energy input rather than releasing energy. The core can no longer generate pressure to resist gravitational collapse. In less than 1 second, the core implodes. Shrinking from a region thousands of kilometers across to a neutron star, perhaps 20 kilometers in diameter. The sudden halt creates a shockwave that rebounds outward, tearing through the star's outer layers and ejecting them into space at velocities exceeding 30,000 kilometers per second. This is a supernova. The supernova serves multiple purposes in cosmic evolution. First, it disperses the heavy elements created during the star's lifetime, enriching the interstellar medium with carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements necessary for planet formation. Second, it creates even heavier elements through rapid neutron capture during the explosion itself, producing gold, platinum, uranium. Third, it compresses nearby clouds of gas through its expanding shock wave, potentially triggering the formation of new stars from material enriched by the previous generation. Type O stars are rare. They represent only 0.00003% of all stars in the Milky Way galaxy. Out of approximately 200 billion stars, only about 60,000 are Type O. Yet despite their rarity, Type O stars have an outsized influence. Their ultraviolet radiation ionizes vast regions of space. Their stellar winds shape the structure of the interstellar medium. Their supernova explosions inject energy and heavy elements into the galaxy, driving chemical evolution and triggering new episodes of star formation. Without Type O stars, the universe would be a fundamentally different place. The interstellar medium would be colder and denser. Nebulae would not glow with ionized gas. The chemical enrichment necessary for rocky planets would proceed much more slowly. Life as we know it requires carbon, oxygen, nitrogen, phosphorus, sulfur, and trace amounts of dozens of heavier elements. Every one of those elements heavier than helium was created inside stars and dispersed through space when those stars died. Type O stars, despite their brief lives, contribute disproportionately to this chemical enrichment. Because they create large amounts of heavy elements and die in violent explosions that efficiently mix those elements into the interstellar medium. But there is a darker implication hidden in the physics of Type O stars. If you were an intelligent species that evolved on a planet orbiting a Type O star, you would face an existential deadline. Your star would die within a few million years of forming. Complex multicellular life on Earth took approximately 600 million years to evolve from simple organisms. Mammals required 220 million years to evolve from the first synapsids. Humans evolved from our last common ancestor, with chimpanzees over approximately 6 million years. None of this evolutionary timeline would fit within the lifetime of a Type O star. This means that Type O stars are fundamentally incompatible with biological evolution as we understand it. They die before life has time to develop. Beyond the simplest bacterial forms, if life can emerge at all in the intense radiation environment surrounding massive hot stars, the habitable zones around Type O stars would be located at enormous distances from the star to avoid being sterilized by ultraviolet radiation. But at those distances, the intense stellar winds and radiation pressure might prevent planets from forming stable orbits. The paradox of Type O stars is that they are essential for creating the heavy elements necessary for life, but they themselves cannot host life. Every Type O star currently burning in the Milky Way will be dead within 10 million years. Most will be dead within 1 million years. They are temporary phenomena, brilliant and brief, existing only to forge heavy elements and scatter them through space via supernova explosions. They are the universe's foundries, operating at maximum temperature for minimum duration, producing the raw materials for everything that comes after them. The closest Type O star to Earth is Zeta Ophiuchi at 366 light-years, far enough that its eventual supernova will pose no direct threat to our planet. But other Type O stars in our galactic neighborhood may not be so benign. Betelgeuse, while classified as a red supergiant rather than a Type O star, was once a Type O star earlier in its evolution. It will explode as a supernova within the next 100,000 years, possibly much sooner. When it does, it will become as bright as the full moon in our night sky, visible even during daytime for several weeks. The explosion will pose no threat to Earth at its distance of 640 light-years, but it will serve as a reminder that stellar evolution is not a theoretical process. It is happening right now, all around us, governed by physics that does not care about observers. Type O stars are cosmic predators. They consume their fuel at unsustainable rates. They dominate their environments through radiation and stellar winds. And they die in explosions that can trigger or destroy the next generation of star formation. They are not gentle. They are not stable. They are not suitable hosts for life. But they are essential for creating the universe we inhabit, a universe where rocky planets can form from heavy elements, and where biological chemistry can operate using carbon, oxygen, and nitrogen. The blue giants burn bright and die fast. And in their death, they make everything else possible. Type B stars are the workhorses of cosmic violence. They are not as hot as Type O stars. They are not as massive. They do not die as quickly. But there are far more of them, and their collective influence shapes the visible structure of every galaxy in the universe. When you look at photographs of spiral galaxies and see brilliant blue spiral arms threading through clouds of pink and red nebulae, you are seeing Type B stars at work. They are the illuminators, the ionizers, the sculptors of interstellar space. And they outnumber Type O stars by more than 100 to 1. Type B stars are defined by surface temperatures ranging from 10,000 to 30,000 Kelvin. Their spectral signatures show neutral helium lines rather than the ionized helium lines characteristic of Type O stars. This single detail reveals a fundamental truth about stellar physics. Small changes in temperature produce dramatic changes in atomic behavior. At 30,000 Kelvin, helium atoms are stripped of their electrons. The boundary between Type O and Type B stars is not arbitrary. It is written into the quantum mechanics of helium ionization. The mass range for Type B stars spans from 2.1 solar masses to 16 solar masses. This range is crucial because it defines stars that are massive enough to burn hot and bright, but not so massive that they exhaust their fuel in cosmically brief timescales. A typical Type B star will live for 10 million to 100 million years depending on its mass. The smallest B-type stars, just above 2 solar masses, can survive for several hundred million years. This extended lifespan means Type B stars have time to migrate away from their birth clusters, spreading throughout galactic disks and contributing to the overall stellar population in ways that Type O stars, with their brief million-year lifetimes, cannot. Rigel is the most famous Type B star visible from Earth, located approximately 860 light-years away in the constellation Orion. When you see Orion in the winter sky, Rigel appears as a brilliant blue-white star, noticeably different in color from the red supergiant Betelgeuse. This color difference is temperature. Rigel burns at approximately 11,000 Kelvin. Betelgeuse, despite being far more luminous in total energy output, has a surface temperature of only 3,400 Kelvin. The blue star is hotter. The red star is merely larger. Rigel is classified as a blue supergiant, meaning it has evolved away from the main sequence and expanded to enormous size. Its radius is approximately 78 times that of our Sun. If you placed Rigel at the center of our solar system, its surface would extend beyond the orbit of Mercury and nearly reach Venus. Despite this enormous size, Rigel's mass is only 21 times that of our Sun, meaning it is a diffuse object with an average density far lower than water. The star's luminosity is 120,000 times that of our Sun. It radiates enough energy every second to power human civilization for 50 billion years. But Rigel is not stable. It is a variable star, fluctuating in brightness over periods of approximately 25 days. These fluctuations result from stellar oscillations, vibrations in the star's outer layers as they expand and contract in response to variations in internal pressure. The star is also losing mass through a powerful stellar wind, shedding material at a rate of approximately 10 to the power of -7 solar masses per year. This is 100 times slower than the mass loss rate of Type O stars, but still represents a substantial flow of material into the surrounding interstellar medium. Rigel will die in a supernova explosion. The exact timing is uncertain because astronomers do not know precisely how much mass the star has already lost through stellar winds. And mass loss affects the evolutionary timeline. Current estimates suggest Rigel will explode within the next million years, possibly much sooner. When it does, it will briefly become one of the brightest objects in the night sky, potentially reaching magnitude -11, bright enough to cast shadows at night and be visible during the day. The explosion will pose no threat to Earth at its distance of 860 light-years. But it will be spectacular. Spica is another prominent Type B star, located 250 light-years away in the constellation Virgo. Spica is actually a binary system consisting of two Type B stars orbiting each other with a period of just 4 days. The primary star is classified as Type B1, with a mass of approximately 11 solar masses and a surface temperature of 22,400 Kelvin. The secondary star is slightly cooler at 18,800 Kelvin, with a mass of approximately 7 solar masses. The two stars are so close together that they are tidally distorted into ellipsoidal shapes, each stretching toward the other due to mutual gravitational attraction. The Spica system demonstrates an important principle of stellar evolution. When stars exist in close binary systems, they can interact in ways that fundamentally alter their evolutionary paths. As the more massive star in the Spica system evolves and begins to expand, it may overflow its Roche lobe, the gravitational boundary beyond which material will fall toward the companion star rather than remaining bound to the primary. When this happens, material will stream from the evolved star to its companion, potentially creating an accretion disk and altering the mass ratio. This mass transfer can dramatically affect the final fate of both stars. Type B stars play a crucial role in creating the visual structure of galaxies. The spiral arms visible in galaxies like the Milky Way, Andromeda, and countless others are not permanent structures. They are density waves, regions where stars and gas temporarily accumulate. Due to gravitational perturbations from galactic rotation patterns. As material moves through these density waves, it gets compressed, triggering episodes of star formation. The newly formed stars include large numbers of hot, massive O and B-type stars. These stars illuminate the spiral arms, making them visible as bright blue tracers threading through the galactic disk. But here is the critical detail. Spiral arms are ephemeral. The density waves that create them propagate through the galactic disk at speeds different from the orbital velocities of individual stars. A star might enter a spiral arm, remain there for a few tens of millions of years, and then exit back into the interarm region. As the density wave moves on, Type O stars, with their lifetimes of only a few million years, rarely leave the spiral arms where they formed. They are born, they live, and they die all within the same spiral structure. But Type B stars, with their longer lifetimes, can survive long enough to exit the spiral arms and enter the interarm regions. This means that Type B stars contribute to the overall blue color of galactic disks, not just the spiral arms. The evolutionary path of Type B stars depends critically on their initial mass. A 2-solar mass B-type star will remain on the main sequence for approximately 2 billion years, gradually fusing hydrogen into helium in its core. When the core hydrogen is exhausted, the star will begin fusing hydrogen in a shell surrounding the core, causing the outer layers to expand. The star will become a subgiant, then eventually a red giant, as it expands to many times its original radius. The core will contract and heat up until it becomes hot enough to fuse helium into carbon and oxygen through the triple alpha process. After helium exhaustion, stars in this mass range do not have enough gravity to ignite carbon fusion. The core becomes an inert carbon-oxygen sphere, surrounded by shells burning helium and hydrogen. Eventually, the outer layers will be expelled as a planetary nebula, leaving behind a white dwarf. A 10 solar mass B-type star follows a more violent path. It remains on the main sequence for approximately 30 million years. Like the lower mass star, it expands into a red giant phase as it burns hydrogen in a shell. But when helium fusion ignites in the core, the star has enough mass and internal temperature to continue through multiple fusion stages. After helium exhaustion, the core contracts until it is hot enough to fuse carbon into neon and magnesium. Then oxygen fusion begins, producing silicon and sulfur. Finally, silicon fusion creates iron peak elements. At this point, the core can no longer generate energy through fusion. It collapses in less than 1 second, rebounds, and explodes as a Type II supernova. The boundary between these two evolutionary paths occurs at approximately 8 solar masses. Stars above this mass threshold will die in supernova explosions. Stars below this threshold will die as planetary nebulae surrounding white dwarfs. This boundary is not sharp. It depends on factors including the star's initial composition, its rotation rate, whether it exists in a binary system, and how much mass it loses through stellar winds during its lifetime. But approximately 8 solar masses represents the dividing line between quiet death and violent explosion. Type B stars contribute significantly to the chemical enrichment of galaxies. Even stars that do not explode as supernovas still produce heavy elements. When these stars expel their outer layers as planetary nebulae, they return carbon, nitrogen, oxygen, and other fusion products to the interstellar medium. The more massive Type B stars that do explode as supernovas contribute even more heavy elements, including iron, nickel, and elements beyond iron, that are created through neutron capture during the explosion itself. The distribution of Type B stars within galaxies reflects their formation history. In spiral galaxies like the Milky Way, Type B stars concentrate in the disk, particularly in spiral arms where active star formation occurs. The galactic halo, consisting of older stars that formed when the galaxy was young, contains very few Type B stars, because those that formed billions of years ago have already died. In elliptical galaxies, where star formation ceased billions of years ago, Type B stars are essentially absent. The stellar population consists of older, cooler stars that formed in the galaxy's youth and have survived to the present day. Achernar is another notable Type B star, located approximately 139 light-years from Earth in the constellation Eridanus. What makes Achernar particularly interesting is its rotation rate. The star spins so rapidly that it is oblate, meaning its equatorial radius is approximately 56% larger than its polar radius. The star is literally flattened by centrifugal force, resembling a squashed sphere. This rapid rotation affects the star's temperature distribution. The poles are hotter and brighter than the equator because the flattening at the equator increases the distance from the core to the surface, allowing more cooling before radiation escapes. The rapid rotation of Achernar raises questions about its formation. Did the star form with high angular momentum, or did it accrete a companion star and gain angular momentum through the merger process? Observations suggest Achernar may be part of a binary system with a much fainter companion. If confirmed, this would support the merger hypothesis. Stellar mergers are thought to be common in dense stellar environments like open clusters, where close gravitational encounters can force binary systems to merge into single, rapidly rotating stars. Type B stars also play a role in ionizing the interstellar medium. While they are not as effective as Type O stars at producing ionizing ultraviolet radiation, their greater numbers mean they collectively contribute substantial amounts of ultraviolet photons to the galactic environment. These photons ionize hydrogen atoms in nearby gas clouds, creating H2 regions that glow in the characteristic red light of hydrogen alpha emission. The Orion Nebula, while primarily ionized by Type O stars in the trapezium cluster, also receives significant ionizing radiation from the numerous Type B stars scattered throughout the region. The stellar winds from Type B stars while less powerful than those from Type O stars, still contribute to shaping the interstellar medium. A typical Type B star might lose 10 to the power of -8 to 10 to the power of -7 solar masses per year through its stellar wind, over the star's lifetime of tens of millions of years. This adds up to approximately 0.1 to 1 solar mass of material returned to the interstellar medium. This material is enriched with the products of CNO cycle fusion, particularly nitrogen, which is produced in abundance in the envelopes of massive stars. The study of Type B stars has revealed important details about stellar evolution and nucleosynthesis. Observations of B-type stars in various evolutionary stages, from main sequence to supergiant to supernova progenitor, allow astronomers to test theoretical models of stellar structure and evolution. Discrepancies between observations and models have led to refinements in our understanding of convection, mass loss, rotation, and binary interactions, all of which affect how stars evolve. Type B stars represent a critical transition in the stellar mass function. They are common enough to significantly affect galactic evolution, but massive enough to burn through nuclear fuel rapidly and contribute to chemical enrichment. They illuminate spiral arms and make galaxies visible across cosmic distances. They produce the ultraviolet radiation that ionizes nebulae and triggers new generations of star formation. And when they die, whether in planetary nebulae or supernova explosions, they return processed material to the interstellar medium, enriching it for the next generation of stars and planets. The universe produces Type B stars continuously in regions of active star formation. In the Milky Way, approximately 100 Type B stars form every year, compared to only a few Type O stars. Over the galaxy's lifetime, billions of Type B stars have formed, lived their brief lives, and died, each one contributing to the gradual chemical enrichment that has transformed the galaxy from a hydrogen-helium cloud into a complex ecosystem containing stars, planets, and at least one form of intelligent life. Without Type B stars, galaxies would be fundamentally different. Spiral arms would be dimmer and less distinct. The rate of chemical enrichment would be slower. Type B stars are the backbone of galactic structure, the illuminators of cosmic architecture, the bridge between the rare, brilliant Type O stars and the more common but cooler stars that dominate the stellar population. The blue-white stars burn hot and die young, but not as hot or as young as their Type O cousins. And in that middle ground, between extreme violence and relative stability, they become the engines that drive galactic evolution forward. The brightest star in Earth's night sky is a lie. Sirius dominates the winter sky with an apparent magnitude of -1.46. Twice as bright as any other star visible to the naked eye. Ancient civilizations worshipped it. Egyptian calendars were organized around its heliacal rising. The moment when Sirius first became visible in the dawn sky after a period of being hidden by the sun's glare. The flooding of the Nile coincided with this astronomical event, leading Egyptians to associate Sirius with the goddess Sopdet, bringer of the new year. The star was so important that the Great Pyramid of Giza contained shafts precisely aligned with Sirius and other significant stars. But here is what the Egyptians did not know. Sirius is not particularly luminous. It appears bright only because it is close. A mere 8.6 light-years from Earth. In terms of actual energy output, Sirius produces only 25 times more light than our Sun. Compare this to Rigel, the Type B star discussed earlier, which generates 120,000 times more light than our Sun, but appears fainter because it lies 860 light-years away. Sirius dominates our sky through proximity, not power. Sirius is a Type A star defined by surface temperatures ranging from 7,500 to 10,000 Kelvin. Its spectrum shows strong hydrogen-Balmer absorption lines, the signature feature that defines the A-type spectral class. These lines appear when hydrogen atoms absorb photons at specific wavelengths corresponding to electron transitions between the second and higher energy levels. Type A stars sit at the sweet spot where Balmer absorption reaches its maximum strength. The discovery of Sirius's true nature required understanding stellar parallax. the apparent shift in a star's position when observed from different points in Earth's orbit around the Sun. Friedrich Wilhelm Bessel accomplished this measurement in 1838. Using a heliometer at the Königsberg Observatory to detect Sirius's parallax of 0.379 arcseconds. This measurement revealed that Sirius was approximately 8.6 light-years distant, making it one of the nearest stars to our solar system. The calculation was revolutionary. For the first time, humans could measure cosmic distances and begin understanding the true scale of stellar luminosities. But Bessel discovered something else while measuring Sirius's position. The star's motion across the sky was not smooth. It wobbled slightly, oscillating around its mean path with a period of approximately 50 years. Bessel concluded that Sirius must have an invisible companion, a dark star whose gravitational influence caused the visible star to wobble. He published this hypothesis in 1844, predicting that a companion star would eventually be discovered. 18 years later, in January 1862, Alvin Graham Clark was testing a new 18.5-inch refracting telescope at the Dearborn Observatory when he spotted a faint point of light near Sirius. This was Sirius B, the white dwarf companion that Bessel had predicted through mathematical analysis alone. The discovery of Sirius B revolutionized astronomy because it revealed a completely new type of stellar object. White dwarfs are the remnant cores of dead stars. Compressed to incredible densities by gravity after the outer layers have been expelled. Sirius B contains approximately 98% of our Sun's mass, compressed into a sphere roughly the size of Earth. This gives it an average density of approximately 2.5 million times that of water. A teaspoon of Sirius B's material would weigh approximately 5.5 tons on Earth. The star's surface gravity is approximately 350,000 times stronger than Earth's. If you stood on the surface of Sirius B, which you cannot because you would be crushed instantly, you would weigh approximately 35 million times your Earth weight. Sirius B is the fate awaiting Sirius A billions of years from now. Type A stars with masses ranging from 1.4 to 2.1 solar masses are not massive enough to explode as supernovas. They will die quietly, swelling into red giants, expelling their outer layers as planetary nebulae, and leaving behind white dwarf cores that will cool slowly over trillions of years. Sirius A has a mass of approximately 2.06 solar masses, just barely below the threshold where supernova explosions become possible. When it dies in approximately 660 million years, it will create a brief but beautiful planetary nebula, before fading to a white dwarf slightly more massive than Sirius B. Vega is another famous Type A star, located 25 light-years from Earth. Vega has special significance in astronomy because it serves as the zero point for the apparent magnitude scale, when astronomers defined the modern magnitude system. They set Vega's apparent magnitude to exactly 0 across all wavelengths. Every other star's brightness is measured relative to Vega. Vega is notable for several reasons beyond its role as the magnitude standard. First, it rotates extremely rapidly, completing one rotation every 12.5 hours. This is approximately 274 times faster than our Sun's rotation rate. The rapid rotation flattens the star at its poles, creating an oblate spheroid. Vega's equatorial radius is approximately 19% larger than its polar radius. This oblateness creates a temperature difference of approximately 2300 Kelvin between the poles and the equator. The poles, being closer to the core, are hotter and emit more radiation. The equator, being farther from the core, is cooler and dimmer. Second, Vega is surrounded by a debris disk, a flat disk of dust and possibly small rocky bodies orbiting the star. The disk was discovered in 1983 by the infrared astronomical satellite, which detected excess infrared emission from Vega. This excess emission comes from dust grains warmed by the star's radiation. The dust extends from approximately 70 to 120 astronomical units from Vega, roughly the distance of the Kuiper belt in our solar system. The dust's presence suggests that either planets are forming around Vega, or that planets have already formed and are perturbing comets and asteroids, creating collisional debris similar to our zodiacal light. The debris disk around Vega raises tantalizing questions about planetary systems around Type A stars. Are such systems common? Can planets form in the intense radiation environment near a hot A-type star? Can life evolve on planets orbiting stars that burn so much hotter than our Sun? The answers remain uncertain, but observations are beginning to provide clues. Several Type A stars, including Fomalhaut and Beta Pictoris, are known to host debris disks and confirmed planets. This suggests that planet formation around Type A stars is not only possible, but potentially common. Altair is the third star in the famous Summer Triangle asterism, along with Vega and Deneb, located 16.7 light-years from Earth. In the constellation Aquila, Altair is another rapidly rotating Type A star. It spins even faster than Vega, completing one rotation in approximately 9 hours. This extreme rotation rate creates such severe oblateness that the star's equatorial diameter is approximately 25% larger than its polar diameter. Like Vega, this creates a significant temperature difference between poles and equator, with the poles being approximately 2000 Kelvin hotter. The rapid rotation of many Type A stars is not fully understood. Stars form from collapsing clouds of gas that possess some initial angular momentum. As the cloud collapses, conservation of angular momentum causes it to spin faster, similar to how figure skaters spin faster when they pull their arms inward. But most stars do not retain all of this angular momentum. They lose it through magnetic braking, a process where magnetic fields couple the star's rotation to stellar winds, gradually slowing the star's spin over time. Type A stars, however, have relatively weak magnetic fields compared to cooler stars. This means magnetic braking is less efficient, allowing Type A stars to retain higher rotation rates. The rapid rotation affects more than just the star's shape. It also affects how the star evolves. Rotation generates mixing in the stellar interior, transporting material between different layers. This mixing can bring fresh hydrogen fuel from the outer layers down into the core region, extending the star's main sequence lifetime. It can also transport fusion products from the core outward, affecting the star's surface composition. In extreme cases, rapid rotation can trigger instabilities that cause the star to shed mass through equatorial winds, losing angular momentum and slowing down over time. Type A stars have been critical to our understanding of stellar evolution because they are common enough to study in detail but evolve quickly enough that we can observe stars at various evolutionary stages. The Hyades star cluster, located approximately 153 light-years from Earth in the constellation Taurus, contains numerous Type A stars at various points in their evolution. The cluster is approximately 625 million years old, meaning its most massive stars have already evolved away from the main sequence and become giants by studying the distribution of stars in the Hyades. On a Hertzsprung-Russell diagram, astronomers can test theoretical models of stellar evolution and determine the cluster's age with reasonable precision. The chemical composition of Type A stars reveals important details about galactic chemical evolution. These stars formed from gas that had already been enriched by previous generations of massive stars. Their spectra show absorption lines from heavy elements including iron, calcium, magnesium, and dozens of others. The strength of these metal lines varies from star to star, reflecting differences in the composition of the gas clouds from which they formed. Stars in the galactic halo, which formed when the galaxy was young and metal poor, show much weaker metal lines than stars in the galactic disk, which formed more recently from gas enriched by billions of years of stellar nucleosynthesis. Some Type A stars display peculiar abundances of certain elements. These chemically peculiar A stars, or AP stars, show enhanced abundances of elements like europium, chromium, strontium, and rare earth elements in their atmospheres. The enhancements can be factors of 100 to 1,000 times higher than normal. The explanation involves magnetic fields. AP stars typically have strong, ordered magnetic fields, unlike normal Type A stars which have weak or negligible fields. These magnetic fields affect how atoms diffuse through the stellar atmosphere. Light elements like helium and nitrogen can radiatively levitate to higher atmospheric layers, while heavy elements sink downward. or get trapped at specific atmospheric levels. The result is a highly stratified atmosphere with unusual abundance patterns. The brightness of Type A stars makes them valuable for measuring cosmic distances because many Type A stars are visible at great distances. They can be used as standard candles for determining the distances to star clusters and nearby galaxies. The technique involves measuring the star's apparent brightness. And spectroscopic type, using theoretical models to estimate its absolute brightness, and then using the inverse square law to calculate its distance. This method, called spectroscopic parallax, has been essential for mapping the structure of the Milky Way and determining distances to nearby galaxies. Type A stars also play a role in the search for extraterrestrial intelligence. Several SETI surveys have targeted nearby Type A stars, under the assumption that advanced civilizations might develop around stars slightly more luminous than our Sun. The logic is that more luminous stars have larger habitable zones, potentially allowing for more planets at comfortable temperatures. However, this advantage is offset by shorter stellar lifetimes. A 2 solar mass Type A star will remain on the main sequence for only approximately 1 billion years, compared to 10 billion years for a solar-type star. This shorter time span reduces the window for intelligent life to evolve, making Type A stars less attractive targets for SETI despite their brightness. The study of Type A stars has also contributed to our understanding of stellar pulsations. Several subclasses of variable stars fall within the Type A spectral range. Delta sky variables are Type A stars that pulsate with periods of 1 to 5 hours and brightness variations of a few tenths of a magnitude. These pulsations result from acoustic oscillations in the stellar envelope, similar to how a bell rings after being struck, by analyzing the pulsation frequencies. Astronomers can probe the internal structure of these stars, testing theoretical models of stellar structure in ways that are impossible for non-pulsating stars. Cepheid variables, which are crucial distance indicators in cosmology, also pass through the Type A spectral class during their pulsation cycles. As a Cepheid expands and contracts, its surface temperature changes, causing it to oscillate between spectral types. At maximum brightness, a Cepheid might be Type F. The regularity of Cepheid pulsations combined with their high luminosity makes them invaluable for measuring distances to galaxies. The lifetime of Type A stars ranges from 400 million to 2 billion years depending on mass. A 1.4 solar mass A-type star will remain on the main sequence for approximately 2 billion years before exhausting its core hydrogen and beginning its evolution toward the red giant phase. A 2.1 solar mass A-type star will last only approximately 400 million years on the main sequence. This mass dependence creates a clear correlation between stellar mass and lifetime. More massive stars burn through their fuel faster and die younger. When Type A stars die, they do not explode. Their masses are below the threshold of approximately 8 solar masses necessary for core collapse supernovas. Instead, they follow the planetary nebula pathway. As core hydrogen is exhausted, the star begins burning hydrogen in a shell around the core. This shell burning causes the outer layers to expand, transforming the star into a subgiant and eventually a red giant. The core contracts and heats until helium fusion ignites through the triple alpha process, converting helium into carbon and oxygen. After helium exhaustion, the core again contracts, but the star's mass is insufficient to ignite carbon fusion. The core becomes an inert carbon-oxygen sphere. As the star continues losing mass through stellar winds during its red giant phase, the core is eventually exposed. The ejected outer layers form an expanding shell of gas illuminated by ultraviolet radiation from the hot core. This is a planetary nebula. Glowing clouds of ionized gas surrounding white dwarf remnants. The nebula expands for tens of thousands of years before dispersing into the interstellar medium, enriching it with carbon, nitrogen, oxygen, and other elements synthesized during the star's lifetime. The white dwarf core cools over trillions of years, gradually fading from white to yellow to red to black as it radiates away its residual thermal energy. Type A stars represent a middle ground in stellar evolution. They are hot enough to be visibly blue-white to the human eye, distinguishing them from yellow-white F-type stars and yellow G-type stars like the Sun. They are massive enough to burn brightly and evolve relatively quickly. but not so massive that they die in violent explosions. They occupy a comfortable position in the stellar hierarchy, visible, numerous, and long-lived enough to be studied. The apparent permanence of stars like Sirius is an illusion. They shine brightly enough to dominate our sky, creating the impression of eternal constancy. Ancient civilizations saw the same stars we see, arranged in the same constellations, and concluded that the heavens were unchanging. But that constancy is temporary. Sirius is approximately 242 million years old. It will remain on the main sequence for another 660 million years. Then it will expand, fade, and die, leaving behind a white dwarf that will slowly cool for trillions of years until it becomes a black dwarf. A theoretical stellar remnant, so cold it no longer emits visible light. Every Type A star in the night sky is temporary. Everyone is dying. The process is slower than for Type O or Type B stars, slow enough that human civilizations can rise and fall without noticing any change. But the countdown continues regardless of whether anyone is watching. The brightest star in our sky today will not exist in its current form 1 billion years from now. And the civilization that watches Sirius die, if any such civilization exists, will see a very different night sky than the one we see. Populated by different stars at different evolutionary stages, continuing the endless cycle of stellar birth and death. Type A stars are the illusionists of the cosmos. They shine bright enough to seem important, to anchor our constellations, to earn names and mythological significance. But they are neither the most powerful stars nor the most common. They are merely the ones that happen to be bright enough and close enough to catch our attention. And in catching that attention, they teach us that brightness does not equal significance, that proximity creates false impressions, and that everything we see in the night sky is temporary. The white stars shine and slowly die, leaving behind dense corpses that will outlive the universe's current age. There is a category of stars that nobody talks about. They are not hot enough to be spectacular. They are not cool enough to be common. They do not explode as supernovas. They do not live long enough to witness the heat death of the universe. They occupy a narrow temperature band between 7,500 and 6,000 Kelvin, a mere 1,500-degree range that makes them the astronomical equivalent of middle management. Nobody writes epic mythology about Type F stars. Nobody names spacecraft after them. They are the forgotten stars, the overlooked majority. The cosmic bureaucrats keeping the galaxy running while everyone pays attention to the brilliant blue giants and the familiar yellow suns. But here is what the textbooks will not tell you. Type F stars represent the most important transition zone in stellar evolution. They are the boundary between two fundamentally different types of stellar structure. On the hot side, stars have radiative envelopes where energy transport occurs, through photons bouncing between atoms. On the cool side, stars have convective envelopes where energy transport occurs through physical circulation of hot gas. Rising and cool gas sinking, Type F stars sit precisely at this boundary, possessing shallow convection zones that are just beginning to develop. This makes them laboratories for understanding how stellar structure changes with temperature and mass. The spectral characteristics of Type F stars show evidence of this transitional nature. Their spectra contain strong hydrogen bomber lines inherited from hotter Type A stars, but also show weakening lines of ionized calcium, the H and K lines that become dominant in cooler stars. This mixture of hot star and cool star features makes Type F stars immediately recognizable to spectroscopists. Procyon is the most famous Type F star visible from Earth, located 11.46 light-years away in the constellation Canis Minor. Procyon serves as the little dog star, in contrast to Sirius, the dog star proper. The name derives from the Greek prokion, meaning before the dog, because Procyon rises shortly before Sirius in the night sky. With an apparent magnitude of 0.34, Procyon is the 8th brightest star visible from Earth. Procyon is classified as Type F5, meaning it sits near the cool end of the F-type range. Its surface temperature measures approximately 6,530 Kelvin, making it noticeably hotter than our Sun's 5,700 Kelvin but substantially cooler than Type A stars. The star has a mass of approximately 1.499 solar masses. But Procyon, like Sirius, has a secret. It, too, possesses a white dwarf companion, designated Procyon b. The companion was predicted through astrometric measurements in 1840 by Friedrich Bessel, the same astronomer who predicted Sirius B. The wobble in Procyon's proper motion indicated an unseen companion with an orbital period of approximately 40.8 years. The companion was not actually observed until 1896, when John Martin Chabrol finally spotted it using the 36-inch refractor at Lick Observatory. Procyon b has a mass of approximately 0.602 solar masses, compressed into a sphere slightly larger than Earth. The existence of Procyon b tells us something important about Type F stars. They are not primordial objects. They did not form in their current configuration. Procyon A and Procyon B formed together as a binary system approximately 1.87 billion years ago. Initially, Procyon b was the more massive star. It evolved faster than its companion, exhausting its hydrogen fuel, expanding into a red giant, and eventually expelling its outer layers as a planetary nebula. The remnant core became the white dwarf we see today. Meanwhile, Procyon A continued burning hydrogen on the main sequence, gradually evolving toward higher luminosity as it ages. This evolutionary history reveals a critical aspect of stellar astrophysics. What we observe today is not what existed in the past. Binary systems evolve. The more massive star always dies first, leaving its companion to orbit a white dwarf remnant. Eventually, Procyon A will follow the same path, swelling into a red giant and ejecting its own planetary nebula. The system will then consist of two white dwarfs orbiting each other, slowly cooling over trillions of years until they fade from visibility. Canopus is another prominent Type F star, though its classification is complicated. Located approximately 310 light-years from Earth in the constellation Carina, Canopus is the second brightest star in Earth's night sky after Sirius. But unlike Sirius, which appears bright due to proximity, Canopus is genuinely luminous. The star generates approximately 10,600 times more light than our Sun. If Canopus were placed at the same distance as Sirius, it would appear approximately 73 times brighter than Sirius appears now. Canopus is classified as Type F0, placing it at the hot end of the F-type range just below Type A stars. But the star is not on the main sequence. It is a bright giant, meaning it has already exhausted the hydrogen in its core and is now burning hydrogen in a shell around the core. The star's radius is approximately 71 times that of our Sun. Its mass is estimated at approximately 8.5 solar masses, placing it near the boundary where stars transition from planetary nebula death to supernova death. The fate of Canopus is uncertain. If its mass exceeds 8 solar masses, it will explode as a Type II supernova, scattering its contents across dozens of light-years, and leaving behind either a neutron star or black hole remnant. If its mass is below 8 solar masses, it will die more quietly. The uncertainty arises because we cannot measure the star's current mass with sufficient precision and because mass loss through stellar winds. Polaris, the North Star, is another Type F star with evolutionary complications, located approximately 323 light-years from Earth. Polaris sits almost exactly at the North Celestial Pole, the point in the sky directly above Earth's North Pole. This makes Polaris appear stationary while other stars rotate around it due to Earth's rotation. Navigators have used Polaris for thousands of years. But Polaris is not actually stationary in space. It appears stationary only from Earth's perspective due to the coincidence that Earth's rotational axis currently points. This alignment is temporary. Earth's axis precesses, completing one full cycle every approximately 25,772 years. 13,000 years ago, the star Vega was the North Pole star. 13,000 years from now, Vega will again be the North Pole star. Polaris's reign as the North Star is a temporary circumstance that will last only a few more centuries before precession moves Earth's axis away from it. Polaris is classified as Type F7, placing it near the cool end of the F-type range. Like Canopus, Polaris is not a main sequence star. It is a supergiant, evolved far beyond its main sequence lifetime, currently burning helium in its core while burning hydrogen in a shell. The star has a mass of approximately 5.4 solar masses and a radius approximately 37.5 times that of our Sun. Polaris is also a variable star, specifically a Cepheid variable. It pulsates with a period of approximately 3.97 days, varying in brightness by approximately 0.1 magnitudes. This pulsation results from a feedback mechanism in the star's helium ionization zone. As the star contracts, the helium ionization zone becomes denser and more opaque, trapping radiation and causing the zone to expand. As it expands, the zone becomes less dense and more transparent, allowing radiation to escape and causing the zone to contract. The cycle repeats continuously, creating periodic variations in the star's size, temperature, and brightness. The importance of Cepheid variables to cosmology cannot be overstated. In 1912, Henrietta Swan Leavitt discovered that Cepheid variables show a precise relationship between their pulsation period and their absolute brightness. Longer period Cepheids are more luminous than shorter period Cepheids. This period luminosity relationship means that by measuring a Cepheid's pulsation period, you can determine its absolute brightness. By comparing the absolute brightness to the apparent brightness, you can calculate the distance using the inverse square law. This technique allowed Edwin Hubble to measure the distances to nearby galaxies in the 1920s, proving that the universe extends far beyond the Milky Way, and ultimately discovering that the universe is expanding. Type F stars have masses ranging from 1.04 to 1.4 solar masses. This mass range determines their main sequence lifetimes, which span from approximately 2 to 4 billion years depending on specific mass. A 1.04 solar mass F-type star will remain on the main sequence for approximately 4 billion years before exhausting its core hydrogen. A 1.4 solar mass F-type star will last only approximately 2 billion years. This lifetime is long enough for planets to form, and potentially for life to evolve, but shorter than the lifetime of G-type stars like our Sun. The question of habitability around Type F stars is actively debated among astrobiologists. On one hand, Type F stars are more luminous than the Sun, meaning their habitable zones are located farther from the star. This increased distance potentially reduces tidal locking problems that plague planets around cooler, fainter stars. The higher luminosity also means the habitable zone is wider, potentially allowing multiple planets to orbit at comfortable temperatures. On the other hand, Type F stars have shorter lifetimes than the Sun. Complex multicellular life on Earth took approximately 600 million years to evolve from simple organisms. Intelligent life required even longer. A civilization developing around an F-type star would have less time to evolve before their star leaves the main sequence and begins its transformation into a red giant. Type F stars also emit more ultraviolet radiation than the Sun due to their higher surface temperatures. This increased UV flux could be beneficial or harmful to life, depending on the planet's atmospheric composition and magnetic field strength. Moderate UV radiation can drive photochemistry and potentially accelerate the emergence of organic complexity. But excessive UV radiation can damage DNA and prevent life from emerging in the first place. The balance depends on details that we cannot yet measure for most exoplanetary systems. Several confirmed exoplanets orbit Type F stars. HD 102317b is a hot Jupiter orbiting an F-type star, approximately 154 light-years from Earth. The planet has a mass approximately 0.45 times that of Jupiter, and orbits its host star every 4.1 days at a distance of approximately 0.052 astronomical units. This extreme proximity means the planet's surface temperature exceeds 1000 Kelvin, far too hot for life as we know it. But the existence of this planet confirms that gas giant formation can occur around Type F stars, and where gas giants exist, smaller rocky planets might also exist. HD 10647b is another exoplanet orbiting an F-type star, this one located approximately 108 light-years from Earth. The planet is a super-Earth with a mass approximately 6.7 times that of Earth, orbiting its host star every 28.34 days. The planet's orbital distance places it well within the habitable zone, where liquid water could exist on the surface if the planet has an appropriate atmosphere. This makes HD 10647b one of the potentially habitable exoplanets discovered to date, though confirming whether the planet actually hosts liquid water would require detailed atmospheric observations that are beyond current technological capabilities. The convection zones that begin to appear in Type F stars have important implications for stellar activity. Convection generates magnetic fields through dynamo processes, where the motion of ionized gas creates electrical currents. These magnetic fields can emerge through the stellar surface as sunspots, regions of concentrated magnetic flux that are cooler and darker than the surrounding photosphere. They can also drive stellar flares, sudden releases of magnetic energy that heat coronal gas to millions of Kelvin and eject charged particles into space. Type F stars show modest magnetic activity compared to the Sun. Their convection zones are shallower, producing weaker dynamos and less frequent flares. This reduced activity might be beneficial for habitability. Solar flares on the Sun can disrupt satellite operations, damage electrical grids. For planets orbiting close to cool M-type stars, stellar flares can be intense enough to strip away atmospheric gases, potentially preventing the development of stable atmospheres necessary for life. Type F stars, with their moderate activity levels, might provide a more stable environment. The chemical composition of Type F stars reflects their formation from gas enriched by previous generations of stars. Their spectra show absorption lines from dozens of elements, including iron, calcium, magnesium, sodium, silicon, and others. The strength of these metal lines varies depending on when and where the star formed. Stars in the galactic halo, which formed billions of years ago from metal-poor gas, show weak metal lines. Stars in the galactic disk, which formed more recently from gas enriched by billions of years of stellar nucleosynthesis, show stronger metal lines. This metallicity gradient allows astronomers to infer stellar ages and formation locations from spectroscopic observations alone. Type F stars occupy a peculiar position in galactic ecology. They are common enough to contribute significantly to the total stellar population. They are luminous enough to be visible at substantial distances, but not so luminous that they die quickly. They are hot enough to ionize surrounding gas, but not so hot that they dominate the galactic radiation field. They are the middle children of the stellar family, overshadowed by their more brilliant older siblings and their more numerous younger siblings. The evolution of Type F stars follows the same general pattern as Type A stars. After exhausting core hydrogen, they burn hydrogen in a shell around the core, causing the outer layers to expand into the subgiant phase. When the core becomes hot enough, helium fusion ignites. Through the triple alpha process, after helium exhaustion, the core again contracts, but most Type F stars do not have sufficient mass to ignite carbon fusion. The star expels its outer layers as a planetary nebula, leaving behind a white dwarf core that cools over trillions of years. The planetary nebula created by dying Type F stars are less spectacular than those created by more massive stars, but they are more numerous. Because Type F stars live longer than Type O, B, and A stars, more of them reach the planetary nebula phase during any given time period. The nebulae typically last approximately 10,000 to 20,000 years before dispersing, during which time they enrich the interstellar medium. Type F stars represent approximately 3% of all main sequence stars in the Milky Way. This makes them less common than G, K, and M type stars, but more common than A, B, and O type stars. In absolute numbers, the galaxy contains approximately 6 billion Type F main sequence stars. Each one is burning hydrogen, evolving slowly toward higher luminosity and eventually approaching the end of its main sequence life. Every year, approximately 1,000 Type F stars in the Milky Way exhaust their core hydrogen and begin transitioning to the red giant phase. Every year, approximately 1,000 Type F red giants expel their outer layers and become planetary nebulae surrounding white dwarf cores. The neglect of Type F stars in popular astronomy reflects a broader pattern in how humans understand the cosmos. We focus on extremes. We study the hottest stars, the largest stars, the most violent explosions, the most exotic remnants. We overlook the middle ground. But these transition objects often contain the most important physics. They show us how properties change continuously across parameter space. rather than jumping discontinuously between categories. Type F stars teach us that stellar classification is not about discrete types, but about continuous variation. A spectrum of properties that changes smoothly from the hottest O-type stars to the coolest M-type stars. The forgotten stars shine yellow-white in the night sky, ignored by mythmakers and casual observers alike. But they are there, burning steadily, hosting planets perhaps, providing stable environments where life might emerge. They are the transitions, the boundaries, the definitions of where one type of stellar physics ends and another begins. And in their overlooked middle ground, they remind us that the universe does not organize itself for human convenience. It creates continuous variation, and we impose categories for our own understanding. The yellow-white stars burn and slowly die, transitioning from one phase to another. Occupying the space between spectacle and stability, you are alive because of a mathematical coincidence. The star that keeps you from freezing to death sits in the exact middle of the stellar classification system, burning at precisely 5700 Kelvin, radiating exactly the right amount of energy to warm Earth's surface to temperatures where liquid water can exist. If our Sun were 10% more massive, it would burn as a Type F star, exhausting its hydrogen fuel in 6 billion years instead of 10 billion years. Complex life on Earth would not have had time to evolve. If our Sun were 10% less massive, it would burn as a Type K star, dimmer and cooler, forcing Earth to orbit closer to maintain habitable temperatures. At that reduced distance, tidal forces would eventually lock Earth's rotation to its orbital period. But our Sun is neither 10% more massive nor 10% less massive. It sits at exactly one solar mass, the reference point against which all other stellar masses are measured. It burns at type G2, the spectral classification that defines what a middle-aged, hydrogen-burning star looks like when everything goes right. And this perfect mediocrity is the only reason you exist. Type G stars are defined by surface temperatures ranging from 5300 to 6000 Kelvin. Their spectra show relatively weak hydrogen Balmer lines compared to hotter stars, but prominent absorption lines from neutral and singly ionized metals. The most distinctive features are the calcium H and K lines at 393.4 and 396.8 nanometers. The Sun has been studied more intensively than any other star in the universe. We know its mass to 9 significant figures, 1.98847 times 10. We know its radius to 4 significant figures, 696,000 kilometers. We know its luminosity to 5 significant figures. We know the composition of its photosphere, approximately 73.46% hydrogen by mass, 24.85% helium. We know these details because the Sun is the only star we can study at close range, the only star whose surface features we can resolve spatially. But here is what most people do not understand. The Sun you see today is not the Sun that illuminated Earth 4 billion years ago. Stars evolve even while burning hydrogen on the main sequence. As the Sun fuses hydrogen into helium in its core, the helium accumulates. This makes the core denser and hotter, which increases the fusion rate, which increases the luminosity. The Sun is approximately 30% more luminous today than it was when it first reached the main sequence 4.6 billion years ago. This gradual brightening creates a problem called the faint young sun paradox. 4 billion years ago, when the Sun was 30% fainter, Earth should have been frozen solid. The reduced solar luminosity would have placed Earth outside the habitable zone, turning it into an ice world with surface temperatures well below the freezing point of water. Yet, geological evidence clearly shows that liquid water existed on Earth's surface. Sedimentary rocks from that era require liquid water to form. Fossil evidence of early life dates back at least 3.5 billion years. And life as we know it requires liquid water. Something kept Earth warm despite the fainter Sun. The solution involves greenhouse gases. Earth's early atmosphere contained much higher concentrations of carbon dioxide and methane than today's atmosphere. These gases trapped infrared radiation, warming the surface through the greenhouse effect and compensating for the reduced solar luminosity. As the Sun gradually brightened over billions of years, Geological processes removed carbon dioxide from the atmosphere through weathering and carbonate formation, reducing the greenhouse effect to prevent overheating. This negative feedback mechanism, where increasing solar luminosity triggers processes that remove greenhouse gases, has maintained Earth's surface temperature within the habitable range for 4 billion years, but this feedback will not last forever. The sun continues brightening at a rate of approximately 1% per 100 million years. In approximately 1 billion years, the increased solar luminosity will evaporate Earth's oceans regardless of atmospheric composition. The water vapor will rise into the stratosphere, where ultraviolet radiation will split the molecules, allowing hydrogen to escape to space. While oxygen reacts with surface rocks, Earth will transform into a hot, dry desert world resembling Venus. This represents the end of the habitable period for Earth, occurring long before the Sun leaves the main sequence. The fact that Earth has remained habitable for 4 billion years despite the Sun's increasing luminosity is not guaranteed for all planets orbiting Type G stars. The feedback mechanisms that stabilized Earth's climate involve plate tectonics, which recycle carbon between the atmosphere and the mantle through volcanic outgassing and subduction. Not all rocky planets have plate tectonics. Venus apparently lacks active plate tectonics, which may explain why it experienced a runaway greenhouse effect that boiled away its oceans and transformed it into the hellscape we observe today, with surface temperatures exceeding 730 Kelvin. Alpha Centauri A is another Type G star, the closest one to Earth besides our Sun, located approximately 4.37 light-years away in the constellation Centaurus. Alpha Centauri A forms a binary system with Alpha Centauri B, an orange K-type star. The two stars orbit their common center of mass. At closest approach, they are separated by approximately 11.2 astronomical units, similar to the distance between the Sun and Saturn. At their widest separation, they are approximately 35.6 astronomical units apart, slightly beyond the orbit of Neptune. Alpha Centauri A is classified as Type G2, identical to our Sun's classification. Its mass is approximately 1.0793 solar masses. The star is slightly older than our Sun, with an estimated age of 4.85 billion years compared to the Sun's 4.6 billion years. In 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri, a red dwarf that is the third member of the Alpha Centauri system. Proxima Centauri b is a potentially Earth-sized planet orbiting within the habitable zone of its host star. But Proxima Centauri is a Type M star, and the habitability of planets orbiting M-type stars is questionable due to stellar flares and tidal locking issues. The question of whether planets orbit Alpha Centauri A or B themselves remains open. Detecting Earth-sized planets around nearby stars is technically challenging. Tau Ceti is another nearby Type G star, located approximately 11.9 light-years from Earth in the constellation Cetus. Classified as Type G8, Tau Ceti sits near the cool end of the G-type range, close to the boundary with Type K stars. The star is approximately 5.8 billion years old, making it slightly older than our Sun. Tau Ceti has been a target for SETI observations. In 2012 and 2017, astronomers announced the possible detection of multiple planets orbiting Tau Ceti, including at least 2 planets that might orbit within the habitable zone. However, these detections remain controversial because they are based on subtle radial velocity signals that are difficult to distinguish from stellar activity. The importance of Type G stars to astrobiology cannot be overstated. Life on Earth evolved around a Type G star. The energy flux, the UV radiation environment, the stellar stability, and the 10 billion-year main sequence lifetime all contributed to creating conditions where life could emerge and evolve over billions of years. When scientists search for potentially habitable exoplanets, they often focus on planets orbiting Type G stars. But Type G stars are not particularly common. They represent approximately 7.6% of all main sequence stars in the Milky Way. This means approximately 15 billion Type G stars exist in the galaxy, a substantial number in absolute terms, but a small fraction. Compared to the dominance of cooler K and M-type stars. If habitability requires type G stars, then the number of potentially habitable worlds is limited by the rarity of this stellar type. However, recent research suggests that habitability is not limited to planets orbiting type G stars. Type K stars, which are slightly cooler and more numerous than type G stars, might actually provide better conditions for life. K-type stars have longer main sequence lifetimes, giving life more time to evolve. They are less active than M-type stars, reducing the risk of atmospheric stripping by stellar flares. And they are common, meaning that if K-type stars can host habitable planets, the number of potentially habitable worlds in the galaxy increases substantially. This realization has shifted the focus of exoplanet searches toward K-type stars in recent years. The solar neutrino problem plagued astrophysics for more than 30 years and was ultimately solved through understanding particle physics rather than stellar physics. Fusion reactions in the Sun's core produce electron neutrinos, nearly massless particles that interact so weakly with matter that they pass through the entire Sun without being absorbed. These neutrinos travel to Earth at nearly the speed of light. Beginning in the 1960s, Raymond Davis constructed a neutrino detector in the Homestake gold mine in South Dakota, using a tank containing 615 tons of perchloroethylene cleaning fluid. Davis's detector measured approximately 1/3 of the expected neutrino flux from the Sun. This discrepancy, known as the solar neutrino problem, suggested that either our understanding of solar fusion was wrong, or our understanding of neutrino physics was incomplete. The solution involved neutrino oscillations. Neutrinos come in 3 flavors: electron neutrinos, muon neutrinos, and tau neutrinos. If neutrinos have mass, which was not certain in the 1960s, they can oscillate between flavors as they travel through space. The Sun produces electron neutrinos through fusion, but during the 8-minute journey from the Sun's core to Earth. Some of these electron neutrinos oscillate into muon or tau neutrinos. Davis's detector was only sensitive to electron neutrinos, so it missed the neutrinos that had oscillated. Later experiments using detectors sensitive to all 3 neutrino flavors confirmed that the total neutrino flux matches solar models when oscillations are accounted for. This resolution demonstrated that the Sun's fusion processes are well understood and provided evidence that neutrinos have mass, a discovery that won the Nobel Prize in Physics in 2015. The Sun's magnetic field drives solar activity, including sunspots, solar flares, and coronal mass ejections. The field is generated by a dynamo process in the convection zone. These fields emerge through the photosphere as sunspots, regions where concentrated magnetic flux suppresses convection and reduces the local temperature. Sunspot numbers vary on an approximately 11-year cycle discovered by Samuel Heinrich Schwab in 1843 after 17 years of daily solar observations. At solar minimum, the Sun may be spotless for days or weeks. At solar maximum, dozens or hundreds of sunspots may be visible simultaneously. The cycle is not perfectly regular. The physical mechanism driving the cycle involves the winding and unwinding of magnetic field lines by differential rotation, where the Sun's equator rotates faster than its poles. Solar flares and coronal mass ejections can affect Earth when they are directed toward our planet. The energetic particles and radiation can disrupt satellite operations, interfere with radio communications, damage electrical grids, and increase radiation exposure for astronauts and high-altitude aircraft crews. The largest recorded solar storm, the Carrington event of September 1859, produced auroras visible as far south as the Caribbean and caused widespread telegraph system failures. A similar event today would cause trillions of dollars in damage to modern technological infrastructure. Other Type G stars presumably have similar magnetic cycles. Though observing stellar activity on other stars is more difficult because we cannot resolve surface features spatially, astronomers monitor stellar brightness variations and chromospheric emission to infer activity levels. Some Type G stars show regular activity cycles similar to the Sun's 11-year cycle. Others show irregular variability or no detectable cycle. The reasons for this diversity are not fully understood, but probably involve differences in rotation rate. The Sun will remain on the main sequence for approximately another 5 billion years. During this time, it will continue brightening gradually. Earth will become uninhabitable in approximately 1 billion years, as the increasing luminosity evaporates the oceans and triggers a runaway greenhouse effect. By approximately 3 billion years, Earth will resemble Venus, with surface temperatures hot enough to melt lead and an atmosphere of carbon dioxide. When the Sun exhausts the hydrogen in its core approximately 5 billion years from now, it will begin burning hydrogen in a shell around the core. This shell burning will cause the outer layers to expand, transforming the Sun into a red giant with a radius approximately 250 times larger than today. The Sun's luminosity will increase to approximately 3,000 times its current value. Mercury will be engulfed by the expanding photosphere and vaporized. Venus will likely suffer the same fate. Earth's fate is uncertain. The Sun will lose approximately 30% of its mass through stellar winds. This mass loss will cause Earth's orbit to expand, potentially carrying it beyond the Sun's surface. But even if Earth escapes engulfment, the intense heat will vaporize any remaining atmosphere and melt the surface. After approximately 100 million years as a red giant burning hydrogen, the Sun's core will become hot enough to ignite helium fusion through the triple alpha process. This ignition will occur explosively in a helium flash, where the entire core fuses helium to carbon and oxygen in a runaway reaction that releases approximately 10 to the power of 44 joules of energy in a few seconds. From the outside, the helium flash is not directly visible. The Sun will settle into a new equilibrium, burning helium in the core and hydrogen in a shell. The helium burning phase will last approximately 100 million years, after which the core helium will be exhausted. The Sun will again expand. As it burns helium in the shell around the carbon-oxygen core, this second red giant phase, called the asymptotic giant branch phase, will see the Sun expand to approximately 370 times its current radius, and increase in luminosity to approximately 5,200 times its current value. Strong stellar winds will strip away the outer layers at a rate of approximately 10 to the power of -7 solar masses per year. Eventually, the entire hydrogen and helium envelope will be ejected, exposing the hot carbon-oxygen core to space. Ultraviolet radiation from the core will ionize the ejected envelope, creating a planetary nebula that will glow for approximately 10,000 years before dispersing. The core will remain as a white dwarf with a mass of approximately 0.6 solar masses compressed into a sphere approximately the size of Earth. The white dwarf will cool over trillions of years, gradually fading from white to yellow to red to black as it radiates away its residual thermal energy. This is the fate awaiting every Type G star. They burn steadily for 10 billion years, providing stable environments where planets can form, and potentially where life can evolve. Then they expand, destroy their inner planets, expel their outer layers, and fade into white dwarf remnants. The entire process is deterministic, written into the physics of stellar evolution, immune to intervention or prevention. Type G stars represent a cosmic sweet spot. They are hot enough to have large habitable zones extending over substantial orbital distances. They are cool enough to burn slowly. They have convection zones deep enough to generate magnetic fields and drive stellar activity, but not so deep that the activity becomes violent enough. They are massive enough to produce all the elements up to iron through fusion, but not so massive that they explode as supernovas before life has time to evolve. But this sweet spot is narrow. A slight increase in mass transforms a Type G star into a Type F star with shorter lifetime. A slight decrease in mass transforms it into a Type K star with reduced luminosity. The range of masses that produce Type G stars spans only from 0.8 to 1.04 solar masses, a mere 24% variation. Within this narrow range, nature has created stars that burn at exactly the right rate to allow 10 billion years of stability. The fact that we evolved around a Type G star does not mean Type G stars are the only stars capable of hosting life. The universe might be filled with civilizations that evolved around Type K stars or Type F stars, or even Type M stars under conditions we do not yet understand. But we know with certainty that life can evolve around at least one Type G star, because we are the proof. And that single data point suggests that other Type G stars in the galaxy might host similar processes. Planets where liquid water exists, where organic chemistry operates, where evolution has billions of years to produce complexity. The golden stars burn with perfect mediocrity. Neither too hot nor too cold, neither too bright nor too dim, neither too stable nor too variable. They are the accident of habitability, the cosmic coincidence that made consciousness possible, and in 5 billion years, they will destroy everything they created. The best stars for life are the ones nobody is looking at. For decades, astronomers searching for habitable exoplanets focused their attention on Type G stars. The logic seemed sound. Life evolved around a Type G star, therefore, Type G stars must be optimal for life. But this reasoning contains a fatal flaw. It assumes that the star around which we happen to evolve represents the best possible stellar environment for biological complexity. It assumes that our existence around a Type G star is a sign of optimization rather than coincidence. Type K stars demolish these assumptions. They are cooler than the Sun, with surface temperatures ranging from 3700 to 5300 Kelvin. They are fainter, producing only 13 to 79% of solar luminosity depending on their mass. They are more common than Type G stars, representing approximately 12% of all main sequence stars in the Milky Way. They live longer, remaining on the main sequence for 15 to 30 billion years. Compared to the Sun's 10 billion years. This combination of properties makes Type K stars potentially superior hosts for life. They provide stable environments for longer periods than Type G stars. They are numerous enough that planets orbiting them should be common. And they are just energetic enough to maintain habitable zones at distances where tidal locking is not guaranteed. Alpha Centauri b is the nearest Type K star to Earth, forming a binary system with the Type G star Alpha Centauri a. Located 4.37 light-years away, Alpha Centauri b is classified as Type K1, placing it near the hot end of the K-type range. Its mass is approximately 0.9073 solar masses, and its luminosity is approximately 0.50 times solar luminosity. The star's surface temperature measures approximately 5,260 Kelvin, noticeably cooler than our Sun's 5,700 Kelvin, but still hot enough to appear distinctly orange to the human eye. The binary nature of the Alpha Centauri system raises questions about planetary formation and stability. Can planets form in binary systems where two stars orbit each other? Can they maintain stable orbits over billions of years despite gravitational perturbations from both stars? Theoretical calculations suggest that planets can exist in two stable configurations. They can orbit one of the stars in a close orbit, remaining gravitationally bound to that star while the companion star's influence remains relatively minor. Or they can orbit both stars in a wide circumbinary orbit. For Alpha Centauri, this means stable orbits exist within approximately 3 astronomical units of either star, encompassing the entire habitable zone of both Alpha Centauri A and B. Epsilon Eridani is another nearby Type K star located 10.5 light-years from Earth in the constellation Eridanus. Classified as Type K2, Epsilon Eridani is cooler than Alpha Centauri b with a surface temperature of approximately 5,084 Kelvin. Its mass is approximately 0.82 solar masses, and its luminosity is approximately 0.34 times solar luminosity. The star is significantly younger than our Sun, with an estimated age of only 400 million to 800 million years. This youth is evident in the star's high activity level. Epsilon Eridani exhibits strong chromospheric emission, indicating an active magnetic dynamo. In 2000, astronomers announced the discovery of a planet orbiting Epsilon Eridani. Designated Epsilon Eridani b, the planet has a mass of approximately 0.78 Jupiter masses and orbits at approximately 3.4 astronomical units with a period of approximately 7.4 years. This places the planet beyond the habitable zone, which for a star of Epsilon, Eridani's luminosity lies between approximately 0.5 and 1 astronomical unit, but the existence of a gas giant in the outer system suggests that smaller rocky planets might exist in the inner system, potentially within the habitable zone. Detecting such planets is challenging due to the star's youth and high activity level, which create brightness variations and spectral features. Epsilon Eridani is also surrounded by debris disks, rings of dust, and small rocky bodies similar to our solar system's asteroid belt and Kuiper belt. These disks were detected through infrared excess emission, radiation from dust grains warmed by the star's energy. The inner disk extends from approximately 3 to 20 astronomical units. The outer disk extends from approximately 35 to 90 astronomical units. The gap between the disks might be cleared by additional planets that have not yet been detected. The presence of debris disks indicates that planet formation occurred or is still occurring around Epsilon Eridani. This makes the star a valuable target for studying planetary system development. 61 Cygni is a binary system consisting of two Type K stars, designated 61 Cygni A and 61 Cygni B. Located 11.4 light-years from Earth in the constellation Cygnus, this system holds historical significance. In 1838, Friedrich Wilhelm Bessel measured the parallax of 61 Cygni, making it the first star other than the Sun to have its distance accurately determined. The measurement yielded a parallax of approximately 0.314 arcseconds, corresponding to a distance of approximately 10.4 light-years. This achievement demonstrated that stars are not fixed on a celestial sphere, but are objects at various distances, fundamentally changing our understanding of cosmic scale. 61 Cygni A is classified as Type K5, placing it at the cool end of the K-type range near the boundary with Type M stars. Its surface temperature is approximately 4600 Kelvin, and its luminosity is approximately 0.153 times solar luminosity. 61 Cygni B is slightly cooler at Type K7 with a surface temperature of approximately 4400 Kelvin. The two stars orbit each other with a period of approximately 659 years, with a mean separation of approximately 84 astronomical units. In 2004, astronomers reported the possible detection of a planet orbiting 61 Cygni A. If confirmed, this would make 61 Cygni one of the oldest exoplanetary systems ever claimed, as similar astrometric observations date back more than a century. However, subsequent observations have not confirmed the planet's existence, and the detection remains controversial. The difficulty in confirming or refuting planetary detections around 61 Cygni illustrates the challenges of studying planetary systems around faint stars. The habitability of planets around Type K stars has become a major focus of astrobiology research in recent years. The concept of the K-dwarf opportunity emerged from studies suggesting that Type K stars might provide optimal conditions for the development of complex life. The reasoning involves several factors. First, Type K stars have longer main sequence lifetimes than Type G stars. A 0.8 solar mass K-type star will remain on the main sequence for approximately 17 billion years, compared to 10 billion years for our Sun. This extended lifetime provides more time for life to evolve, from simple organisms to complex multicellular forms to potentially intelligent species. Second, Type K stars are more stable than Type M stars. Red dwarfs, despite their extreme longevity, are prone to violent stellar flares that can strip away planetary atmospheres, particularly for planets in the close-in habitable zones required by such faint stars. Type K stars have lower flare rates and less extreme stellar activity, reducing the risk of atmospheric erosion while still maintaining sufficient convection. Third, Type K stars are numerous. They outnumber Type G stars by approximately 50%, meaning that if planets are equally common around both stellar types, there should be 50% more potentially habitable worlds orbiting Type K stars than Type G stars. This statistical argument alone makes Type K stars attractive targets for habitability studies. Fourth, the habitable zones around Type K stars are located at moderate distances where tidal locking is less likely to occur. For a typical Type K star with 0.5 solar luminosities, the habitable zone extends from approximately 0.7 to 1.2 astronomical units. Planets at these distances will experience tidal forces that gradually slow their rotation over billions of years, but the timescales are long enough. Compare this to Type M stars, where habitable zone planets orbit at only 0.1 to 0.3 astronomical units and become tidally locked. The evolutionary pathway of Type K stars follows the same general pattern as Type G stars, but proceeds more slowly due to lower core temperatures and fusion rates. A typical Type K star will spend 15 to 30 billion years on the main sequence depending on its mass. During this time, it gradually brightens. The brightening rate is slower than for Type G stars, extending the period during which planets can maintain habitable surface temperatures. When a Type K star exhausts its core hydrogen, it begins burning hydrogen in a shell around the core, causing the outer layers to expand. The star's luminosity increases dramatically by factors of 1,000 to 10,000 depending on mass. Planets that were once in the habitable zone are now scorched and sterilized. Planets that were once frozen wastes in the outer system become temporarily warmed, potentially developing liquid water for brief periods before the star's evolution continues. After a hydrogen shell burning, the core contracts and heats until helium fusion ignites, for stars at the low mass end of the K-type range. This ignition occurs explosively in a helium flash similar to what awaits our Sun. The helium flash is not directly visible from outside the star. For stars at the high mass end of the K-type range, approaching 1 solar mass, helium ignition occurs more gently without a flash. During the helium burning phase, the star maintains relatively stable luminosity for approximately 100 million years. Carbon and oxygen accumulate in the core. As helium is converted through the triple alpha process, when core helium is exhausted, the star again expands as it burns helium in a shell. This asymptotic giant branch phase is characterized by strong mass loss through stellar winds. The star sheds its outer envelope at rates of 10 to the power of -7. Eventually, the entire envelope is ejected as a planetary nebula. The hot core, now exposed, ionizes the ejected material through ultraviolet radiation. The planetary nebula expands for 10,000 to 20,000 years before dispersing into the interstellar medium. The core remains as a white dwarf with a mass of approximately 0.5 to 0.6 solar masses, cooling over trillions of years. The metallicity of Type K stars affects their ability to host planets. Stars with higher metal content, meaning higher abundances of elements heavier than helium, are more likely to have planetary systems. This correlation was discovered through exoplanet surveys that found gas giant planets are approximately 3 times more common. The explanation involves planet formation mechanisms. Rocky planets and the cores of gas giants form through the accumulation of solid particles in protoplanetary disks. Higher metal content means more solid material available, accelerating planet formation and increasing the likelihood that planets grow large enough to retain gaseous envelopes. Type K stars in the galactic halo, which formed billions of years ago from metal-poor gas, are less likely to host planets than Type K stars in the galactic disk. This creates a temporal bias in habitability. Early in the galaxy's history, when metal content was low, planetary formation was less efficient. As stellar generations lived and died, enriching the interstellar medium with heavy elements, planetary formation became more efficient. This suggests that the galaxy is becoming more habitable over time as metal content rises, a process that will continue for billions of years. The search for exoplanets around Type K stars has intensified in recent years, as the advantages of these stars for habitability have become clearer. The Transiting Exoplanet Survey satellite, launched in April 2018, is surveying approximately 200,000 nearby stars for transiting planets. Ground-based surveys using radial velocity techniques are also targeting Type K stars. The goal is to identify potentially habitable planets. Where atmospheric characterization might be possible using the James Webb Space Telescope or future extremely large telescopes. Several confirmed exoplanets orbit Type K stars in or near their habitable zones. Kepler 442b is a super-Earth with approximately 5 times Earth's mass. Orbiting a Type K star approximately 1,200 light-years from Earth, the planet orbits within its star's habitable zone with a period of approximately 112 days. Its size suggests it might be a rocky planet with a thick atmosphere, potentially capable of supporting liquid water. Kepler 462b is another potentially habitable exoplanet orbiting a Type K star approximately 1,170 light-years from Earth. The planet has approximately 60% greater radius than Earth and orbits its host star every 267 days. Its location within the habitable zone makes it one of the most Earth-like exoplanets discovered to date, though confirming whether it actually hosts liquid water. Type K stars represent approximately 12% of all main sequence stars in the Milky Way. This corresponds to approximately 24 billion Type K main sequence stars in the galaxy, if even a small fraction of these stars host Earth-sized planets in their habitable zones. The number of potentially habitable worlds orbiting Type K stars could number in the billions. This statistical argument, combined with the extended lifetimes and moderate activity levels of Type K stars, makes them prime candidates for hosting life in the galaxy. But the quiet optimism surrounding Type K stars contains a darker implication. If Type K stars are truly optimal for biological complexity, and if they are more common than Type G stars, then the absence of detectable technological civilizations in our cosmic neighborhood suggests one of several disturbing possibilities. Either intelligent life is extraordinarily rare, even under optimal conditions, or intelligent life is common but short-lived, destroying itself before developing interstellar communication capabilities. Or intelligent life is common and long-lived but chooses or is forced to remain silent. Or we are genuinely alone in the galaxy despite billions of potentially habitable worlds orbiting billions of seemingly suitable stars. The orange stars burn quietly and patiently, outliving their more brilliant siblings, waiting longer for complexity to emerge in their habitable zones. They are the tortoises in a cosmic race where speed kills and patience rewards, and they will still be burning trillions of years from now. Long after every type O, B, A, F, and G star has died, hosting whatever remnants of life and intelligence survive the galaxy's long decline into darkness. The universe belongs to the red dwarfs. This is not speculation. This is mathematics. Type M stars represent 76% of all main sequence stars in the Milky Way. Out of approximately 200 billion stars in the galaxy, 152 billion are red dwarfs. They outnumber every other stellar type combined. They are the cosmic majority, the background radiation of stellar populations, the faint red points that dominate star counts but contribute almost nothing to the visible light we see when we look at galaxies. And they will outlive everything. Type M stars are defined by surface temperatures below 3,700 Kelvin, ranging down to approximately 2,300 Kelvin for the coolest examples. At these temperatures, molecules can exist in stellar atmospheres: titanium oxide, vanadium oxide, water vapor, carbon monoxide, and dozens of other molecular species. Create complex absorption bands in Type M spectra, giving them their characteristic appearance. The light from Type M stars is predominantly red and infrared, with peak emission occurring at wavelengths longer than 700 nanometers, to human eyes adapted for yellow-green light from our Type G sun. Type M stars appear dim and ruddy, barely contributing to the illumination of the night sky. But what Type M stars lack in brightness, they compensate for with longevity. A 0.08 solar mass M-type star, the minimum mass capable of sustaining hydrogen fusion, will remain on the main sequence for approximately 6 trillion years. This is approximately 430 times longer than the current age of the universe. The star will still be burning hydrogen through proton-proton chain reactions long after every type O, B, A, F, G, and K star in the galaxy has died and faded to a white dwarf or neutron star remnant. Type M stars are the torches that will illuminate the universe's final eras, the patient predators that survive through efficiency rather than brilliance. Proxima Centauri is the closest star to our solar system, located 4.244 light-years from Earth. It is a Type M 5.5 red dwarf with a mass of approximately 0.1223 solar masses. If you replaced our Sun with Proxima Centauri, Earth would receive approximately 0.17% as much energy. dropping surface temperatures to approximately 100 Kelvin, cold enough to freeze nitrogen out of the atmosphere. But Proxima Centauri hosts at least 2 planets. Proxima Centauri b, announced in 2016, has a minimum mass of approximately 1.27 Earth masses and orbits within the habitable zone. At a distance of approximately 0.0485 astronomical units. This extreme proximity, approximately 12 times closer than Earth orbits the Sun, is necessary because Proxima Centauri is so faint that its habitable zone lies very close to the star. The planet's orbital period is only 11.186 days. At this distance, tidal forces almost certainly lock the planet's rotation to its orbit, meaning one hemisphere permanently faces the star, while the other freezes in eternal darkness. The habitability of Proxima Centauri b is hotly debated. Tidal locking creates extreme temperature differences. Without a thick atmosphere to redistribute heat, the day side would be scorched while the night side freezes, but atmospheric circulation models suggest that even a modest atmosphere could transport enough heat to moderate temperatures, potentially creating a terminator zone between day and night hemispheres, where temperatures allow liquid water. The greater concern is stellar activity. Red dwarfs are magnetically active, producing frequent flares that emit X-rays and ultraviolet radiation. Proxima Centauri experiences flares that increase its brightness by factors of several percent, sometimes multiple times per day. These flares could strip away planetary atmospheres over billions of years unless the planet has a strong magnetic field to deflect charged particles. In 2020, astronomers announced the discovery of Proxima Centauri c, a second planet orbiting at approximately 1.489 astronomical units. With a period of approximately 1,900 days, roughly 5.3 years, this planet has a minimum mass of approximately 7 Earth masses, making it a super-Earth or mini-Neptune. Its distance from the star places it well outside the habitable zone where surface temperatures are too cold for liquid water. But the existence of a second planet suggests that Proxima Centauri hosts a complete planetary system, possibly with additional undetected planets. Barnard's star is the second closest stellar system to our Sun after Alpha Centauri, located 5.96 light-years from Earth. It is a Type M4 red dwarf with a mass of approximately 0.144 solar masses and a luminosity of approximately 0.004 times solar luminosity. Barnard's star is notable for having the largest proper motion of any star, moving across the sky at 10.3 arcseconds per year. This high proper motion results from the star's proximity and its velocity relative to our solar system of approximately 106 kilometers per second. At its current trajectory, Barnard's star will approach within approximately 3.8 light-years of Earth in approximately 9,800 years before receding again. For decades, astronomers suspected that Barnard's star hosted planets based on apparent wobbles in its proper motion. In 1963, Peter van de Kamp claimed to have detected a Jupiter-mass planet orbiting the star. Subsequent observations failed to confirm this detection, and the claimed wobbles were eventually attributed to instrumental artifacts. But in 2018, astronomers announced the discovery of Barnard's star B. The planet has a minimum mass of approximately 3.23 Earth masses and orbits at approximately 0.4 astronomical units with a period of approximately 233 days. Its location places it near the snowline where water ice can exist, but surface temperatures are approximately minus 170 degrees Celsius, far too cold for liquid water. TRAPPIST-1 is a Type M8 red dwarf, located approximately 40.66 light-years. With a mass of approximately 0.089 solar masses, TRAPPIST-1 is barely above the hydrogen-burning limit. Its luminosity is approximately 0.00054 times solar luminosity, making it one of the faintest stars known to host planets. What makes TRAPPIST-1 extraordinary is not the star itself, but its planetary system. In 2017, astronomers announced that at least 7 Earth-sized planets orbit TRAPPIST-1, designated TRAPPIST-1 B through H. This makes TRAPPIST-1 the star system with the most Earth-sized planets ever discovered. The 7 planets orbit extremely close to their host star. The innermost planet, TRAPPIST-1b, orbits at only 0.01154 astronomical units, completing one orbit every 1.51 days. The outermost planet, TRAPPIST-1h, orbits at 0.063 astronomical units. All 7 planets orbit closer to their star than Mercury orbits our Sun, yet 3 of them, TRAPPIST-1, E, F, and G, orbit within the habitable zone, where liquid water could exist on their surfaces if atmospheric conditions are suitable. The TRAPPIST-1 planets are almost certainly tidally locked. With one hemisphere permanently facing the star, they may experience resonant locking, where orbital periods are related by simple ratios. TRAPPIST-1, B, C, D, E, F, and G have orbital periods approximately in the ratio 8:5 to 3 to 2 to 1.5 to 1, suggesting they formed through disk migration processes that established resonant chains. These resonances mean that planets regularly align in their orbits, creating gravitational interactions that affect their orbital parameters over time. The question of habitability around Type M stars has dominated astrobiology discussions. Red dwarfs present both advantages and challenges for life. The primary advantage is longevity. Type M stars remain on the main sequence for trillions of years, providing stable environments far longer than any other stellar type. If life requires billions of years to evolve complexity, Type M stars offer more time. The high frequency of planets around red dwarfs, demonstrated by surveys showing that most Type M stars host multiple planets, means potentially habitable worlds orbiting red dwarfs vastly outnumber those orbiting larger stars. But the challenges are severe. Tidal locking creates day-night temperature extremes that might prevent liquid water from existing stably unless planets have thick atmospheres capable of heat redistribution. Stellar flares, particularly common during red dwarfs' first 2 billion years when they are magnetically hyperactive, emit radiation that could strip away atmospheres. The faint light from red dwarfs is predominantly infrared, which might limit photosynthesis efficiency if life uses photosynthesis at all. And the close proximity required for habitable temperatures places planets within regions where stellar winds and coronal mass ejections are intense. Recent research suggests some of these challenges might be less severe than initially feared. Tidal locking does not necessarily preclude habitability. Even a relatively thin atmosphere comparable to Earth's might be sufficient to prevent atmospheric collapse on the night side. Magnetic fields generated by planetary dynamos can protect atmospheres from stellar wind stripping and planets with active plate tectonics. Photosynthesis in infrared wavelengths, while less efficient than photosynthesis using visible light, is theoretically possible and might even have advantages. The flare problem remains the most serious concern. During their first 2 billion years, Type M stars experience frequent superflares, with energies exceeding 10 to the power of 33 ergs, approximately 10,000 times more energetic than the largest solar flares observed from our Sun. These superflares emit X-rays and extreme ultraviolet radiation that ionize and heat planetary atmospheres, driving atmospheric escape to space. Models suggest that planets around young red dwarfs could lose Earth mass atmospheres within a few 100 million years unless they possess unusually strong magnetic fields. But after approximately 2 billion years, red dwarfs settle into quieter phases where flare activity decreases substantially. Planets that survive the violent youth of their host stars enter a period of relative stability that can last for trillions of years. This suggests a possible scenario where life on red dwarf planets emerges later than on planets around more massive stars, developing only after flare activity has decreased to manageable levels. If so, the galaxy might be filled with red dwarf planets that are only now, after 10 to 12 billion years of galactic evolution, reaching the point where complex life can begin developing. The mass range for Type M stars spans from approximately 0.08 solar masses to 0.6 solar masses. The lower boundary represents the minimum mass necessary to sustain hydrogen fusion through proton-proton chain reactions. Below this limit, objects are classified as brown dwarfs. Substellar objects that never achieve core temperatures high enough for stable hydrogen burning. Brown dwarfs do fuse deuterium, but deuterium is rare and quickly exhausted, leaving brown dwarfs to slowly cool and fade over billions of years without any internal energy source. The upper boundary of the Type M range transitions into Type K stars at approximately 6,500 Kelvin surface temperature. This boundary is somewhat arbitrary, defined by the appearance of molecular absorption bands in cooler stars. The transition from K to M spectral types represents a shift in atmospheric chemistry, from atomic absorption dominating the spectrum to molecular absorption becoming significant. This chemical transition reflects the fundamental change in stellar structure. Type M stars are fully convective. Unlike more massive stars where energy transport in the outer layers occurs through radiation, Type M stars transport all their energy through convection. Hot plasma rises from deep within the star, cools as it radiates energy, and sinks back down in a continuous circulation pattern. This full convection has important implications. It means the entire stellar interior is well mixed, with fusion products from the core being transported to the surface and fresh hydrogen from the surface being delivered to the core. This mixing extends the star's lifetime by making all of its hydrogen available for fusion, not just the hydrogen initially in the core. Full convection also affects magnetic field generation. The magnetic dynamos in more massive stars operate at the interface between the radiative core and convective envelope. Type M stars lack this interface, requiring a different dynamo mechanism. Observations suggest Type M stars generate magnetic fields through turbulent convection. These fields are typically weaker than those generated by interface dynamos in solar-type stars, but they are present and drive stellar activity, including flares and spots. The luminosity evolution of Type M stars is qualitatively different from more massive stars. When a solar-type star burns hydrogen on the main sequence, helium ash accumulates in the core, increasing the core's mean molecular weight and density. This causes the core to contract and heat. But Type M stars are fully convective, meaning fusion products are mixed throughout the star rather than accumulating in the core. This mixing prevents the concentration of helium ash that drives luminosity evolution in more massive stars. As a result, Type M stars maintain relatively constant luminosity throughout their main sequence lifetimes, brightening by only a few % over trillions of years. When a Type M star finally exhausts all of its hydrogen fuel, it does not expand into a red giant. The star lacks sufficient mass for the core to reach temperatures where helium fusion can ignite. Instead, the star simply contracts, converting gravitational potential energy into heat as it shrinks, eventually electron degeneracy pressure, a quantum mechanical effect where electrons resist being compressed beyond certain densities, halts the contraction. The star becomes a helium white dwarf, a dense remnant composed primarily of helium that was never fused into heavier elements. But this endpoint lies trillions of years in the future. No Type M star in the universe has yet exhausted its hydrogen fuel. The oldest Type M stars formed approximately 13 billion years ago during the galaxy's youth, have consumed less than 1% of their available hydrogen. They will continue burning for trillions of years more, long after the sun has died, long after Earth's orbit has decayed through gravitational wave emission, long after the Milky Way and Andromeda have merged into a single elliptical galaxy. The universe's far future belongs to Type M stars. In 100 billion years, star formation in the Milky Way will have ceased. As gas is consumed and locked into stellar remnants, the galaxy's stellar population will consist of white dwarfs, neutron stars, black holes, and red dwarfs. In 1 trillion years, the last Type O, B, A, F, G, and K stars will have died, leaving only Type M stars still burning hydrogen. These faint red embers will illuminate a galaxy otherwise dark except for the faint glow of cooling white dwarfs. In 100 trillion years, even the longest-lived Type M stars will approach hydrogen exhaustion. The universe will enter what cosmologists call the degenerate era, where stellar remnants outnumber active stars by vast ratios. The last stars will flicker out, leaving a cosmos populated by white dwarfs, neutron stars, black holes, and planets that have long since frozen solid or been consumed by their dying parent stars. In 10 to the power of 40 years, even protons might decay. If grand unified theories of physics are correct, disintegrating white dwarfs and neutron stars into radiation and leaving only black holes. As the universe's primary massive objects, Type M stars are the universe's method for extracting maximum energy from minimum mass. They burn hydrogen so slowly that they achieve fuel efficiency no other stellar type can match. They are the ultimate expression of stellar optimization, trading luminosity for longevity, brightness for endurance. And in the cosmic long run, endurance wins. Brilliance is temporary. Patience outlasts everything. The statistical dominance of Type M stars carries philosophical implications. Most stars in the universe are small, cool, and faint. Most planets in the universe orbit such stars. If life exists elsewhere in the galaxy, it most likely evolved on a tidally locked world orbiting a red dwarf. Bathed in dim red light, subjected to occasional flares, existing in an environment utterly alien to our Earth-Sun system. Our existence around a Type G star makes us statistical outliers, unusual configurations in a universe that overwhelmingly prefers a different architecture. The red dwarfs burn with patient malice, outlasting every other stellar configuration through sheer endurance. They are the last survivors, the final witnesses. The stars that will see the universe through its transition from the stelliferous era, dominated by active fusion, into the degenerate era. They do not explode. They do not illuminate vast nebulae. They do not dominate their galactic neighborhoods. They simply burn, steadily and quietly. For timescales that dwarf the history of everything that has happened since the Big Bang. And when the last Type M star finally exhausts its hydrogen fuel, in the unimaginably distant future, when the final fusion reaction occurs somewhere in the dying cosmos, when the last light from stellar nuclear burning fades into the darkness, the universe will enter its final epoch. No new stars will form. No new energy sources will ignite. The only light will come from quantum processes. From particle decay if protons are unstable, from Hawking radiation as black holes slowly evaporate over timescales measured in 10 to the power of 100 years. The 7 main types of stars represent the 7 ways the universe has discovered to burn hydrogen into helium, from the brilliant blue Type O giants to the patient red Type M dwarfs burning for trillions of years. Stellar diversity reflects the fundamental relationship between mass, temperature, and fusion rate. More massive stars burn hotter and die faster. Less massive stars burn cooler and survive longer. The spectrum from O to M is a spectrum from violence to patience, from spectacle to endurance, from brightness to darkness. We evolved around a Type G star, a middle-aged yellow dwarf that will provide stable illumination for another 5 billion years before expanding into a red giant and consuming the planet that birthed us. We are temporary inhabitants of a temporary environment, living during the brief window when our star provides habitable conditions, and we are statistical anomalies, existing in a galaxy where most stars are faint red dwarfs that will continue burning long after every Type G star has died. The night sky shows us an illusion. The brightest stars are not the most common. They are simply the ones luminous enough to be visible across vast distances. The true face of the galaxy is revealed only through telescopes sensitive to faint red light, instruments that can detect the countless red dwarfs invisible to naked eyes. When we map the galaxy's stellar population accurately, accounting for selection effects and observational biases, we discovered that the universe is primarily red, primarily faint, and primarily long-lived. This is the final lesson of stellar classification. The categories O, B, A, F, G, K, and M are not equally populated. They form a hierarchy where the rarest stars are the brightest, and the most common stars are the dimmest. Nature prefers efficiency over spectacle. The universe has invested most of its stellar mass in objects that will burn for trillions of years rather than millions. And this preference reveals something fundamental about cosmic optimization. In the long run, the quiet survivors outlast the brilliant flames. The 7 types of stars are 7 timescales of death. From Type O stars exploding after a few million years to Type M stars fading after trillions of years, the stellar classification system is fundamentally a catalog of mortality rates. Every star is dying. The only variable is the timescale. And in understanding these timescales, we understand our own cosmic situation, temporary patterns of complexity. Existing during the brief window when our particular star provides the energy necessary for our existence. The thermonuclear bombs lighting the galaxy are all on countdowns. Some have minutes left, some have centuries, some have trillions of years. But all are counting down. And when the last one detonates or sputters out, when the final fusion reaction concludes, when the last photon of stellar light crosses the cosmic void, the universe will enter its final darkness. Not quickly, not dramatically, but inevitably. The red dwarfs will be the last witnesses to stellar light. They will watch every other star type die and fade. And then, trillions of years from now, they too will exhaust their fuel and join the darkness. The 7 types of stars represent the 7 chapters. In the universe's story of stellar evolution, we are living in Chapter 5, orbiting a Type G star during the cosmos's Middle Age. The final chapters belong to the red dwarfs, and they have barely begun. If you have followed this journey through the 7 stellar types, from the violent blue giants to the patient red dwarfs, hit that like button. If you want to understand more about how the universe uses stars as its primary mechanism, for converting hydrogen into the heavy elements necessary for planets and life, subscribe to this channel, because the cosmic machinery is operating all around you. Every second of every day, burning matter into light across timescales that span from millions to trillions of years, and understanding it means understanding your place in a universe that will eventually belong entirely to the faint red embers that even now dominate the galaxy in numbers, if not in brightness.